Welcome to discussion 30. In today's discussion, we'll talk about section 5.4 on net change and 5.5 on U substitution. So in this video, we'll do some net change examples. So recall that the definite integral from a to b of f prime of t dt. To evaluate this, I can take the antiderivative of f prime, which is f, and I'd have to evaluate it at b, and then minus, and then I plug in a, and I'll get f of a. So if I think about what both sides represent, the left-hand side is an integral of a derivative, and a derivative represents a rate of change. So this is the integral of a rate of change. It's an instantaneous rate of change. Rate of change of the original function would have been f from when t equals a to t equals b. The right-hand side is looking at that quantity f, and then we're plugging in the time b and the time a into it and subtracting. And that tells me the net change. The net change in f, the quantity f, from t equals a to t equals b. Okay, so this is saying that when we take an integral of a rate of change function, that equals the net change in that quantity over whatever our time interval was. Okay, so let's do a practice problem. Let's look at problem number 6 from worksheet 14. Okay, so first I want to give you 8 minutes to try this question. So pause the video in 4, 3, 2, 1. Pause it and try it for 8 minutes. All right, so hopefully you did that. Hopefully you paused it and tried it for about 8 minutes. Let's talk about it now. So the question says a rock is thrown up in the air. It starts at the ground, so h of 0, h here I think represents height. The height when t equals 0 is 0. And the equation for acceleration of the rock is a of t equals negative 10 meters per second squared. And it says it's about this because we're rounding. If this was a physics class, we'd probably use the value negative 9.8, but we're going to use negative 10 for this problem. Note that this does not depend on time. This is just a constant. So this is a constant with respect to time. The initial velocity, v of 0, is 15 meters per second. Part A asks, what does the integral from 0 to 2 of a of t dt represent? And calculate it. So acceleration is the derivative of velocity. And using that result from above, it says that when you take an integral of a derivative, integral of a rate of change of some quantity, that should represent the net change in that quantity. In this case, we're taking the integral of the derivative of velocity. So the antiderivative should be the change in velocity. This is going to be the change in velocity of the rock from the starting time, which was 0, and that's in seconds, from 0 seconds to the ending time was t equals 2 seconds. We could also see that if we had evaluated the antiderivative, because the antiderivative acceleration would have been velocity, and we would have plugged in 2 and 0 to get v of 2 minus v of 0. But doing this is a change in velocity. It's the velocity after 2 seconds minus the velocity after 0 seconds. That's the change in velocity. Okay, so it wants us to compute this now. So this integral will be equal to, I get 0 to 2. My acceleration is negative 10. So we get negative 10 dt. So this antiderivative would be negative 10t. And I got to plug in 2 and 0. If I plug in 2, we'll get negative 10 times 2. And then minus, now I got to plug in 0. So I'll get negative 10 times 0. And if we evaluate this, let's see, this is negative 20. And this represents a change in velocity. So the units of this should be the units of velocity, which in the problem are meters per second. So this is saying that our velocity decreases by 20 meters per second on the interval from when t equals 0 to t equals 2 seconds. Okay, so part B now asks to calculate the velocity as a function of time. So if I want v of t as a function of time, this will be an indefinite integral of acceleration, dt. So we got to do the indefinite integral of -10 dt. Okay, and that's going to be -10t plus c, because the indefinite integral means it's a general antiderivative. So I need to use some of the given conditions to figure out c. So I'm going to use the thing that says v of 0 is 15. So if we use v of 0 is 15, okay, and I plug in 0 for the time, we get v of 0 equals -10 times 0 plus c. And that's supposed to be equal to 15. And this tells me that c is 15. Okay, so if we plug that into our velocity is -10t plus 15. And the units of velocity were meters per second. And that's our velocity function. Okay, part C of this question says, well, what does the integral from 0 to 2 of velocity represent? And calculate it. So this is going to be similar to A. Velocity is the derivative of position. So when I take a definite integral of the rate of change of something, this is the rate of change of position, that's going to be the net change in that original quantity. So this is going to be the change in the position in this question represents the height. So this is going to be the change in the height of the rock from t equals 0 seconds to t equals 2 seconds. Okay, so that's what this thing represents. Then it says to calculate it. So if I calculate it, we get the integral from 0 to 2. My velocity we got in part B. This is -10t plus 15 dt. If I do the antiderivative, we'll get -5t squared plus 15t. Then I have to plug in the 0 and the 2. So plugging 2 in, we'll get -5 times 2 squared plus 15 times 2. And then minus what we get when we plug in 0, which is -5 times 0 squared plus 15 times 0. Okay, and if we simplify this, we'll get -5 times 4, that's -20. 15 times 2, that's 30, so plus 30. And I'll have -0, and this ends up being 10. Okay, so this was the change in the height, and the units of height here were meters, so this is 10 meters. Okay, one other comment I want to make about this is a change in position, or in this case it's the change in height, because our position here represents the height. This is called displacement. So part C is saying that the change in the height, or the displacement over this time interval, is 10 meters. In other words, the height at 2 seconds is 10 meters higher than it was at 0 seconds. Okay, so if we look at part D now, it's asking, what if I wish to calculate the total distance traveled by the rock between t equals 0 and t equals 2? Will that be equivalent to what we got in part C? Explain, and if not, if it's different, how would you calculate it? Okay, so let's think about part D now. So the answer, let me try that better. The answer to part C is the displacement. And displacement is just the change in the position, or in this case it's the change in height. Change in height, or more generally the position of the rock from t equals 0 seconds to t equals 2 seconds. Okay, is that the same thing as just the distance traveled? So for this, I'm going to draw a picture. I'm going to draw a picture to talk about, is there a difference between displacement and distance? So here's the ground. The problem told me that the rock started off on the ground. All right, it tells me that when it said that it starts at the ground. H of 0 is 0. Okay, so it's starting at the ground. All right, and then it gets tossed in the air. So it's going to move up, it's going to move up, it's going to move up until it reaches some high point. So it's moving up till it reaches a high point, and then it's going to start to drop down. So I'm going to draw, and then at some point it reaches the end of the time interval. So this is the starting point. It starts at t equals 0, and it ends at t equals 2. And I know that the height at t equals 2 is going to be higher than the height at t equals 0 because of our answer to part C. In C, we got that the change in height over that time interval was 10 meters. That means it's 10 meters higher at 2 seconds than it was at 0 seconds. Also, how do I know that the rock, so when I know that in general, if I throw a rock in the air, eventually it'll reach a high point and then it'll start to drop. How do we know that it's already reached the point where I got to the high point and then it's dropping? So the high point happens when the velocity is 0. And if I go to my velocity function, let's figure out when that happens. So here's my velocity function. If we were to set this equal to 0, we'd see that this equals 0 when t is 1.5. Okay, so in my picture, the velocity would be 0 when t is 1.5 seconds. Okay, and that happens before we reach t equals 2 seconds. So by 2 seconds, this thing is on its way down. Alrighty, so looking at this picture, the displacement is just the difference in the final position, which was here, and the starting position. So this would be the displacement, this vertical distance. But when we talk about the total distance traveled, that needs to consider the way up and the way down as being positive. So how do we figure that out? The total distance, if I want to set it up with an integral, will be the integral over my time interval, but I need to take the absolute value of velocity. And that'll register each of the movements going up and going down as a positive movement. So that absolute value will count the upwards and downwards movements as positive distances. Okay. So to evaluate this, we need to somehow get rid of these absolute values. Okay, so recall that the absolute value of something I can write as a piecewise function. It equals just the inside if the inside thing, the velocity, is greater than or equal to 0. But if the velocity is less than 0, then when I drop the absolute value, I got to put another negative in front of it to make that thing be non-negative. Okay, so the question I got to ask is, when is our velocity, which was negative 10t plus 15, when is that going to be greater than or equal to 0? Because when it is greater than or equal to 0, I can just drop the absolute value bars and just write what I have, just write my velocity. But when it's less than 0, I'll need to put a negative in front of the whole thing to make it non-negative. Okay, so I need to solve this inequality, and we know how to solve these. We got to do the whole cut point method. I got to figure out when is this equal to 0, and we already figured that out. That equals 0 when t equals 1.5, and I also got to figure out when is it undefined, but this is never undefined. Never undefined, and now we are ready to make a number line. So I'm going to make a number line. Our time in this question sort of starts at 0, so our t values are going to be greater than or equal to 0. Okay, so that's why I'm putting a bracket here, and then I put 1.5 as a tick mark. And I'm going to write my whole velocity function as a row, negative 10t plus 15. And I'll separate out a column here. And if I plug in test points in each interval, like if I plug in 1 and something bigger than 1.5, like 2, into this, when I plug in 1, it'll be positive. If I plug in 2, it'll be negative. Okay, so now I know when my velocity is positive and when it's negative. So what we have to do is we're going to split this integral up into pieces. We'll have one piece from 0 to 1.5. And on that interval, velocity is positive. So I can just get rid of the absolute values and write my velocity. And then plus, on the next interval, from 1.5 to 2, my velocity is negative. So I will have to write a negative sign in front of the velocity when I drop the absolute values to make sure it's non-negative. Okay, so now let's go ahead and plug in our velocities. We get 0 to 1.5. Our velocity function is negative 10t plus 15 dt. Plus this integral will be integral from 1.5 to 2. When I do the negative of velocity, it'll switch these signs. I'll get positive 10t minus 15 dt. So from here, it's just doing an antiderivative and plugging in. So I'm going to write dot, 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 and the rest I want to leave for you as an exercise. So the rest I'm going to leave for you. From here, it's not bad. All right, let's do another practice problem. So this is question number 7 from the worksheet, and it asks the rate of water passing through a pipe is r of t equals 10 plus 5 e to the negative 3t plus 1 minus t squared, that whole thing to the negative 1/2 meters cubed per second. And I want to calculate this integral. So we got this integral from 0 to 1/2 of this whole function, 10 plus 5e to the negative 3t plus, let me bring this whole negative 1/2 power to the denominator. That'll make it a positive 1/2, which I can rewrite as a root 1 minus t squared. So we'll be taking that integral. I want to give you 4 minutes to try this. Pause the video in 4, 3, 2, 1. Pause it and try it for 4 minutes. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about 4 minutes. Let's talk about it now. So let's do this antiderivative. For the 10, I'll get 10t. For the next term, 5 is multiplying this function, and 5 is a constant. So the 5 will stay multiplying the antiderivative of e to the negative 3t. So that's going to be e to the negative 3t. But then to sort of undo what the chain rule would do, if I were to take the derivative of this, I have to multiply by a negative 1/3. Or in other words, I got to divide by negative 3. So why is that? Well, we divide by negative 3 to cancel out the chain rule. Because, for example, if I were to take the derivative of just e to the negative 3t on its own, I would need chain rule. I would get e to the stuff times the derivative of the stuff. Derivative of the exponent is negative 3. But that's not quite right, because my original function doesn't have this extra negative 3. So I need a way to cancel out that negative 3. So I will adjust this. Instead, I'm going to put a negative 1/3 in front. If I did the derivative of negative 1/3, e to the negative 3t. And now when I do chain rule, the negative 1/3 will stay there. And then I'll get times e to the stuff times the derivative of the stuff. The derivative of this exponent is negative 3. But now, those negative 3's will cancel. This one will cancel this one, and I just get that original e to the negative 3t, like I want. Okay, so that's why I got to put that negative 1 over 3 in front. Okay, an antiderivative of 1 over the square root of 1 minus t squared. Got to think back to my antiderivative formulas. This is sine inverse. We get sine inverse of t. I got to plug in 0 and a half into this. Okay, if I plug in a half, I get 10 times a half minus 5/3 e to the negative 3/2 plus sine inverse of a half. And then minus, now I got to plug in 0. Plugging in 0, we'll get 10 times 0 minus 5/3 e to the 0. And then plus sine inverse of 0. Close that bracket. All right, so we got to evaluate 10 times a half is 5. And then we get minus 5/3 e to the negative 3/2. For sine inverse of 1/2, let's recall how we do these. So with sine inverse, it will output an angle. It kind of does the opposite of what a trig function like sine would do. With sine, I input an angle. Sine inverse will output an angle. So when we're wondering what is sine inverse of 1/2, that's equivalent to writing, well, sine of what angle equals 1/2. Okay, so if I use a unit circle for this, I'm going to draw a circle. And recall that to make sure I don't get more than one angle, because I need sine inverse to be a function, so it shouldn't have more than one output, we restricted what the angle could be. And the angle is restricted to be between negative pi over 2 and positive pi over 2 for sine inverse. So that is limited to be from here to here. And on that range of angles, the only thing that works is pi over 6. So this will be pi over 6. And then we'll get minus. The stuff in brackets will be we'll just get minus 5/3. Because sine inverse of 0 would be 0 if I do the same type of thing. Okay, so this ends up being, the double negative becomes a plus. So if I add the 5 to the 5/3 and I get a common denominator, we will get 20/3 and then minus 5/3 e to the negative 3/2 plus pi over 6. Okay, so that's our value. What are the units here? So if I think about the function that we were integrating, r of t is the rate at which water passes through a pipe, and the units are meters cubed per second. So that's a unit of volume over time. So we're doing a definite integral of a rate. This is the rate at which a volume is changing. And when I do that integral, it should just tell me the net change in volume. So the units of this should be units of volume, which are, in this problem, meters cubed. Okay, so that is my answer for what is the quantity with units. But it also asks, what does this represent? And we kind of said that. This is the change in the amount of water, volume in this case, then by amount I mean volume, amount of water that has passed, whoops, let's write that better, that's passed through the pipe from 0 seconds to 1/2 a second. And let me just mention that by amount, I mean the volume.